Hello S-Bears, it's great to see you all again. Today we're going to be talking about the restaurant table problem. Now this is a problem that I came up with, but it's not unfamiliar in mathematics, and there has been some research done into it, as I found out later. But this is a question that I had at the start of the year, and I really wanted to make a video about it ever since I started making my channel. You can even see in my old scribbles where I was trying to figure out this question at first, it was the exact time that I was starting to plan my YouTube channel as well. So this question, I go way back. Today I want to try and tackle this problem with you, but our end goal isn't going to be just finding the solution. We're also going to see at how we can think about this and find ways to solve the problem. Since it's not just a general question that might appear on an exam, it's an actual real-world problem we would have to come up with a solution for. To start, I first want to introduce the problem by giving a small anecdote. At the start of the year, me and my family went out for dinner with some of our friends, and I was feeling very tired with so little energy. I didn't have any social battery with me, and I didn't feel like talking with anyone, which happens to everyone. So that's perfectly fine. But it meant that I was constantly drifting away and thinking about other things. Once we got to the restaurant, we had to ask them for a table for many more people since we were a large group. So they said that's perfectly fine, and they started to rearrange the tables in order to make room for us. And when they were moving around the tables, they had to remove some of the chairs because of the way that they combined the tables. And this got me thinking, I wonder, for any combination of tables, how can we find out how many chairs there are going to be? Now, this is quite an interesting problem in its own right, but the question itself is not well defined. And that's important. When you're trying to solve a question, you need to know what you're talking about. What do I mean by combination of tables? For example, a table can be square, it could be a rectangle and have even more people able to sit at it, or it can even be a triangle shape where only 3 people can sit at it. So we need to define what kind of tables are we talking about. And then also, how are we going to combine these tables? Because there's an infinite number of ways that I can put these together like dominoes. So we need to figure out which way would we like to solve. Now the question that I was trying to solve had to do with square tables, where a square table can have 4 people sitting at the table, 1 on each side. Now the premise was that I could combine these tables into certain combinations, and we can see that some of the sides are now connected, which means that a person can't sit there. So in this case, we can now only have a total of 6 people sitting at this table, even though if we had 2 separate tables, there would be 8. And the last thing we need to define is how am I going to make these combinations of tables, because I could just continue adding a table on and on in a straight line forever, but the specific example I wanted to try and solve was for a spiraling pattern. The premise of this spiral structure I mentioned was that every time we would add a table, we would be spiraling outwards, trying to keep the tables as grouped together as possible. By doing this, I would add a table, then I would maybe move down one. Now there's a gap here, and I want to keep them as clustered as possible, so I go and fill in that gap. Then I can move outwards again, I want to fill in that gap again, and I can continue spiraling outwards and outwards. Here you can see some more examples that I made online, just with more tables and how this pattern would continue. I hope it's clear what happens next. Now, let's go back to our first examples of having just 1 or 2 tables. Here we can see that if we have 1 table, there can be 4 chairs seated around, which makes sense, and that's completely fine. That's our starting point. Now, if we have 2 tables, like we mentioned before, because some of them are connected now, we cannot have seats in those 2 corners. So we lose 2 chairs, and we now have a total of 6 chairs available. What if we were to continue this pattern onwards? Well, if we want to add a new table, say here, we would first have to remove this person's chair. So we've taken 1 chair away. If we now add the table, one of the table sides has been connected to the available space, which means that for this table, we wouldn't be able to add 4 chairs, but only 3. So once we've added 3 extra chairs to this structure, we now see that in total, there has been a 2-chair increase. This means that even though we took away 1 chair, we added 3. So on average, we just added 2 chairs. And that means that now the structure has a total of 8 chairs. That's going to be our first important note. When we're adding a new table and it's sticking out from somewhere, we have to remove a chair, but we're going to always add 3, which means that on average you would add 2 chairs to your structure. But what happens if we add a table to somewhere that isn't sticking out? Say, if we want to put into this corner, which is wedged between 2 other tables, what will happen then? Now this time, to make space for the table, we've had to take away 2 chairs, which makes sense because we need to have this whole gap open to add our next table. For this new table that we added, 2 of the sides are unavailable because they had to connect to the previous 2 tables, which means that only 2 of the sides of the table are available for a chair. Now, since we took away 2 chairs and then we put 2 new chairs, in total, we've basically not changed the amount of chairs, and there are still a total of 8 chairs in the structure. So, whenever there's this sort of corner shape and we add a table, there's not going to be any change in the number of chairs available. So, our little investigation has just told us a little bit more about the structure of our growing tables and how the number of chairs will change. The number of chairs will only change when we're connecting to one side of the table. But if we're connecting to 2 sides, then there's not going to be a change at all. So let's see what this looks like if we continue this pattern for more and more tables. Here we can see I made a list of the number of tables and the number of chairs. Now the number of tables follow this pattern and will be continuing spiraling outwards, and then the number of chairs just says how many spaces are available for the chairs. This pattern is very interesting because what we can notice is that every time we're only ever going up by 2 or by 0, just like we said, which makes sense. But the amount of time that it takes to add 2 keeps increasing because the length of our table combinations keeps increasing. So the number of edges that you have to fill in first before reaching the end and making another one-sided addition has to increase over time, which is quite cool. But what a strange equation. What kind of sequence is this? If I wanted to find an equation for the number of chairs based on the number of tables, how could I do that? Well, it's not an arithmetic sequence because it's not being added by the same time every time. It's either being added by 2 or by 0, but that changes. It's not a geometric sequence because it's not being multiplied by the same amount every time, so it's a new kind of sequence entirely. Now, with the information that we just found is already a lot in order to be able to understand the question and find a solution. But to be honest, I wasn't able to find an answer, but a friend of mine from school was able to, and when I posted this question online, someone was able to send me some very useful links to research papers related to this question. So firstly, let's take a look at my friend's solution, and then let's take a look at the research papers. Now, my friend's solution is a pure stroke of genius, but it's very complicated. And even I don't remember how to understand it because this is something we did at the start of the year. So I don't remember how the formula works exactly, but I would still like to take a look. And the solution to this question for the number of chairs based on the number of tables is this equation. Now, this equation is very big and very complicated, but we can break it down and try to understand some parts of it. So let's take a look at 3 key points that my friend uses in this equation. The first function in my friend's method that I want to discuss is this symbol here, which kind of looks like square brackets but with the top part missing. So what does this mean? Well, we call this the floor function, and it's actually quite simple to understand. All it does is round down any number to the nearest whole number. For example, if I had 2.1, it would round down to 2. If I took the floor of pi, it would round down to 3, because pi is approximately 3.14. It's important to note that this function is special because it doesn't just round numbers, it always rounds them down. So if you were to normally round this to 5, the floor function will always round it downwards to 4. You may think of this function as simply removing the decimal expansion and being left with the integer numbers in front. The second function that I want to discuss in my friend's method is the modulo function. Not modulus, but modulo. Now the modulo function, all it does is find the remainder of a number. For example, if I do 17 mod 4, I would get 1. Why? Because 17 divided by 4 is 4 with a remainder of 1. This function is quite useful in order to find remainders, which is something that my friend uses in their equation. The last thing I want to discuss is something called triangle numbers. Now, triangle numbers are part of the equation, but they don't appear as some sort of function. They are simply numbers that are made from triangles. For example, you can have one dot, which is considered the triangle. Then you can have 3 dots arranged in this structure to look like a triangle, 6 dots like that, 10 dots like this. And can you guess what the next triangular number would be? It would be 15. Now, this function is quite complicated, but in a sense, it's a sort of algorithm. Now, what an algorithm does is it follows a step of instructions in order to arrive to a conclusion. So what this formula basically does is, using triangular numbers in some combination and these rounding functions, it finds the first number in a certain sequence that has a certain number of chairs. For example, if you wanted to find how many chairs there are for a combination of 9 tables, what the algorithm does is it finds out which group 9 is in, which would be the 7, 8, 9 group, where they all have 12 tables. So it searches for the first number, which is 7, and uses its algorithm to find out how many chairs 7 would have, which is 12. And it knows, since 7, 8, and 9 are all in the same group, 9 also must have 12 chairs. Now, there are some finer details, and it is quite complicated to understand, but overall, this formula works very well, but it's quite large. So let's see if we can find a simpler and smaller, more condensed formula. In order to do this, I decided to ask the Math Stack Exchange, which if you haven't heard of and you're a mathematician, I absolutely recommend checking it out. There are hundreds of problems that you can get help with. You can ask your own questions, you can help other people solve questions, and it's just a great way to look and learn some very interesting mathematics, and it really makes you think. I've managed to get a lot of help on past questions that I've had related to maths questions that I couldn't solve because it's still too advanced for me. Now, when I posted this question, I got a response very quickly where someone simply sent me a link to a certain website called OEIS. OEIS stands for the Online Encyclopedia of Integer Sequences. And all that means is it's an encyclopedia, so a sort of digital library, which contains a whole bunch of different sequences of numbers that are whole numbers, integer sequences. It turns out if you have any sequence, all you can do is paste it into this website and they will find the closest match for a sequence that matches what you typed in. So it's possible that the person that sent me this just typed it into the website and got the answer, which is amazing. So what did the website say? When I typed in the first, say, 10 numbers of the sequence, it gave me the answer that I was looking for. Now, this sequence is called the minimal perimeter of polyomino with n-square cells, which sounds a little complicated, but it's basically what we're looking for. And the formula that they had in the website is the number of chairs is equal to 2 times the ceiling of 2 times the square root of the number of tables. Now, there's a new function here, which is the ceiling function, which looks like square brackets, but with the bottom part removed. So can we take a guess on what this might do? If you guess that it rounds up, you'd be absolutely right. All this is sort of the opposite of the floor function. It's the ceiling function and it rounds upwards. And this is a much simpler equation. So it's much easier to understand and use, and probably much more efficient for computers to calculate. In OEIS, they don't just tell you the sequence and the formula for it, they give you a bunch of other information too. For example, the people that have inputted this information into the encyclopedia and a little bit of the history of where they got this formula from. Now, the oldest research paper I could find, which includes this formula, is a research paper done by Frank Harary in the University of Michigan in the United States, and Heiko Harborth in the Technical University of Braunschweig. I hope I pronounced that correctly. I'll link their work in the description. And this research paper was published in 1976. So this problem is quite old, but they call it extremal animals, where these structures of the spiraling pattern of squares, these made out of 2D shapes, they call them animals, which is a very interesting name. And it was very fun to read their research paper. However, it's a little bit outside the scope of my own understanding. so I wasn't really able to figure out how they came across this formula. But when I was reading the research paper, I saw that they used a very famous equation which I really like, and I thought I would share it with you guys to end off the video. This formula that they used in order to find the restaurant table equation was v minus e plus f equals 2. Now, if you recognize this formula, this is Euler's Polyhedron formula, and Euler was a famous mathematician who did way too much work for his time, but he came up with this very simple but elegant equation, which says that the vertices minus the edges plus the faces of any 3D shape will always equal 2. What does this mean? Well, if I take the vertices or the corner of a shape, say this pyramid with 1, 2, 3, 4 vertices, and I subtract the number of edges, which is 1, 2, 3, 4, 5, 6 edges, plus the number of faces, which is 1, 2, 3 at the bottom and the 4th on the back. And if you calculate it, it'll give you 2. And this is true for any 3D shape, and there's a very fun way that you can use this in 2D as well. There's a great proof and use of this in 2 dimensions in a video by 3 Blue 1 Brown, and I absolutely recommend checking it out if you want to learn a bit more about this formula. But in general, this is just a super useful formula to use since it links these 3 important features of any 3D shape. You might feel a little bit disappointed that we never actually solved this problem, but that wasn't my entire goal of this video. I knew that it would be way out of my scope of understanding to try to explain these topics, and my friend's method, they could do a much better job than me. What I wanted to do was introduce you guys to a mathematical method where we research the problem and then we learned a bunch of new formulas, for example, what the floor function is or what modulo is. And we managed to broaden our understanding on mathematical topics so that we might be able to use this knowledge in the future to solve more questions. So I hope that you did enjoy today's video and you learned something new. If you have any more questions or anything else, feel free to contact me or leave a comment. And thank you so much for watching. Until next time.